can hear me, right? It actually sounds pretty loud. Let me dial it back just a little bit. So if I say something crazy today, somebody like stop me, raise your hand or something. I noticed I'm actually starting to become an absent-minded professor. On my way over here, I made a wrong turn. I climbed an extra set of stairs, and I ended up like up there on the 8th floor. I'm like walking down the hallway and say, wait, where's the classroom? Oh, 8th floor. How do I get up here? Okay, so today we're going to switch from randomized algorithms. So randomized algorithms are basically useful data structures. We've actually spent most of our time talking about either specific algorithms or alternatively sort of algorithmic schemes that are useful for like large-scale machine learning. So we started out talking about stream and sort. Then we talked about some variations of that. So we talked about stochastic gradient descent, where you stream through things many times. We talked a lot about MapReduce, which is sort of a parallel version of stream and sort. We talked about data flow language abstractions for that. We talked about parameter mixing, which is kind of like sort of a hybrid between stochastic gradient descent, where you stream through a learning algorithm, and MapReduce, where you do lots of things in parallel. We talked a little bit about some architectures that are designed for basically iterative MapReduce algorithms. So we talked about Spark, and we talked briefly about kind of another competitor system called Flink. So what else is there? So this is actually a pretty good summary of the sorts of techniques that people use in large-scale machine learning nowadays, but there's a little bit more. So it turns out a lot of machine learning algorithms, not all of them, but a lot of them have some commonalities. So a lot of them have the property that each parameter you're updating depends on only a small amount of data. So you can do local computations, but sometimes you don't know exactly. So sometimes the structure of those computations is complex. It's often the case you do some sort of iteration. All right, so a prototypical example of an algorithm that sort of satisfies these constraints would be PageRank. So the PageRank for a node, it locally depends on, so you iterate to find the PageRank, so it's an iterative operation. It depends on the PageRank for a particular page only depends on a few nearby pages. All right, so it just depends on the things that link into it, and really that's it. So PageRank is an iterative algorithm. You can imagine doing it for every node in the graph. We collect some incoming PageRanks, and then we send some outgoing PageRanks. So there's communication going on. It's sparse communication. Each node is only talking to a relatively small number of things. And the things that are communicating, you could kind of think of as living in a graph. All right. Now, when I talked about PageRank, I didn't talk about this as an operation you do on graphs. And perhaps the clarity of the algorithms that I talked about suffered from that. Right? So the PageRank algorithms we talked about before were based on doing stream and sort. And to kind of make that work, what you have to do is you have to stream out. You have to read in and read out a structure which includes the whole graph, all the edges of the graph, and the current annotations on that, the PageRanks. So you do a lot of I/O in an iteration of PageRank using this sort of process. All right. An alternative would be to just try and build a system which operates in parallel on graphs. And it turns out there are lots of algorithms that you can express relatively conveniently in this sort of graph parallel system. So the basic idea in a graph parallel system, and we'll talk about some concrete ones, is that you have a big graph. It's stored in memory, typically in cluster memory. So usually it's distributed across multiple machines. Of course, since this is parallel, we're going to at least have multiple threads accessing the graph. But depending on the size of the graph, it will be distributed on multiple machines. It might also be, it'll certainly be accessed by multiple CPUs, and it might be distributed physically on multiple machines. So what you do with this is you do some sort of node-centric computation. So it's some function that you can define based on the data that's resident in a node, possibly combined with some messages you get from neighboring nodes, okay? So usually in these things, there is some property of the node that changes. Usually the edges don't change, so the connectivity of the graph doesn't change, so the graph itself sort of stays fixed. You're just computing some value that is living at the node. Usually the node updates depend only on their neighbors of the graph. And usually all the node updates are done in parallel, or at least conceptually done in parallel. So that's the basic idea, and we're going to talk about a bunch of different systems that kind of work this way. So this is kind of a whirlwind tour of a bunch of systems. I'm going to start with one which is probably the best known, and certainly as far as I know, the earliest. So this has been around for about 5 or 6 years. So basically, Pregel, the main data structure, is a graph. So a computation is defined as a sequence of supersteps. So in a superstep, you basically do something in parallel on a graph, okay? So what do these supersteps look like? So there's some function that the user defines, all right? And that's applied in parallel at every vertex of the graph, all right? It can access the value stored at that node, and it can, rewrite the value set at that node, okay? There's also messages, okay? So you can send messages from the node you're at to another node. If you know the ID of some fixed sort of collective node, some global node, you can send something to that global node. So you can send messages anywhere you want, okay? Once those messages are sent, you can read messages that have been sent to you sort of in the last round, okay? This is an iterative process, so the algorithms you are iterative. So basically, the other thing each vertex can do is they can basically vote as to whether to keep the computation going or to halt it. So this model is called bulk synchronous processing. So all the vertex operations happen simultaneously. So everybody's working with the current value and the messages from the last iteration. And then all the values get set and changed together, okay? So this is the basic idea of bulk synchronous processing. It's a simple graph algorithm. Again, typically what's happening is the graph is changing over time. It's a mutable structure, but all that changes usually is the vertex value, all right? And there's communication, but the communication is, with a few exceptions, which are not widely used. A lot of simple algorithms you can program up without them. The communication is along edges, okay? So how does this work? There's basically one program which takes the graph and partitions it among workers. So every worker gets a certain set of nodes, and the edges between those nodes, okay? If you're sending messages between two nodes in the same worker, then it's very fast. It's basically just a single compute machine, right? So you're basically sending the messages in one memory space. If you have to go to another partition, okay, that means you're sending a message to another worker, all right? So that's expensive communication. So typically then you're sending a message out to the network and you have all the kind of communication overhead that entails. So basically communication across partitions is expensive. Communication within partitions is cheap. The partitions that you use make a big difference. And Pregel tries to take care of that for you. So in principle, it will sort of choose a good set of partitions that minimize the amount of communication that will happen, and you won't have to think about that. So, so what does this look like more concretely? So here's the API, okay, which looks really ugly because it's C++, so that's what you do. There's basically one function when you're defining a vertex. There's one function called compute. It takes a list of incoming messages, all right, or an iterator over incoming messages. There's a function you can call to tell you what step you're in, what superstep you're in. There's a vertex ID, which tells you basically who you are. You can get a value or you can set your value. All right, you can look at all your neighbors, so you can get all the output edges. And once you've gotten one of those edges, you can send a message to that destination vertex. And you can also vote to halt, all right? So the compute, everyone does the compute step in parallel, all right? It just has this one set of inputs, all right? And so what does vote to halt mean? So I know you guys are all excited about hearing about more voting rules today. There are ways in Pregel and many of these systems that you can exercise fine control over how the iteration gets done. The simplest rule is basically consensus, right? So when everyone says you're going to stop, then you stop, right? So everything has to be converged at all points. And I think you can implement an electoral college or something if you wanted to, but who would? Okay. So let's remind ourselves what PageRank is, and then I'll show you the implementation in Pregel. Okay. So what I suggested is you repeat this step until you converge. So you've got a vector, which gives you a weight for every node, right? You multiply it by W, so this is the transition matrix. So basically, you're taking that weight and you're distributing it across all its neighbors. And then the new weight is C times the unit vector, so everybody gets weight of C, right? And then 1 minus C times all these incoming messages, all right? And there's a way we can do this with a stream and sort kind of thing. The simplest version, you save all the vertex values in memory. So it's not a complicated algorithm, but if you can't store all the vertices in memory, you've got to look at the streaming through the edges, then it gets to be expensive. All right. So this is what it looks like in Pregel. All right. So basically says if you're let's see if you've done less than 30 iterations, you should do the following thing. First, add up all the messages. Right. So you go through loop through your messages, you look at their value, and you put that in a running sum. All right. What we're going to add to the value at this vertex is going to be C. Actually, here we're keeping all the, so the way this particular implementation is set up is that this vector V is always going to sum to 1, right? So this unit vector here is a uniform probability, so this would be, if C is 0.15, this would give you C times U at that node, right? And then you get the other 85%, so 1 minus C times the sum of the messages, okay? And then if you're still processing, so the first 30 iterations, you're going to send messages to your neighbors. So you take your value, you divide it by n because you're distributing it to your n neighbors, okay? And you basically send that message so that they can look at their incoming page ranks on the next time. And otherwise, if it's more than 30 iterations, just say, I'll stop. Okay, so after 30 iterations, everybody ends. So this is basically just doing that iteration a fixed number of times, 30. Okay. Here's another one. Another kind of classic problem that looks nice in this sort of iterative process. So what we're going to do is we're going to pick some particular source node, and we're going to find the length of the shortest path to that node to every, and put that at every point of the graph. Okay, so let's imagine I've got a graph that's like the internet, you know, connection between cities. So how long does it take to get from Pittsburgh to Baltimore? What we'd like to do is like put the actual distance between to Pittsburgh at every city in the United States. That's the basic idea. So what's the compute here? Okay, what we're going to do here is we're going to first compute the minimal distance. So there's a base case. All right, if you are actually the source vertex, so if you're Pittsburgh, your distance to Pittsburgh is 0, right? Otherwise, you know, the worst case is infinity, but we'll go through all the messages and see if there's anything smaller. So if any of the messages has a smaller distance, then we'll put that in, okay? And then if we've actually figured out a shorter distance to get to Pittsburgh by doing this, looking at this minimum distance, we'll save it. Okay, so now I know the shortest way of getting to me from Pittsburgh. All right, and I tell everybody else, it's like, hey, I know how to get to you a little bit more efficiently. All right, so how do I do that? Let's say, you know, I'm Baltimore, and I just figured out, oh, I can get to Pittsburgh like, you know, 200 miles. All right, so I just send it to all my neighbors, like Washington's 50 miles away, and say, hey, you can get to Pittsburgh in 200 miles plus 50. Okay, so you send that message out to all your neighbors. All right, and then you say, this seems wrong here. Where is this? Then you say vote to halt. Looks like everyone's going to vote here. I feel like this should be an else vote to halt, right? So if you haven't done an update, you haven't sent anybody a message, then you can say we're done. If you did send a message, you should say not. I feel like this should be an else. So here's an experiment. So this is a 1 billion node binary tree, okay, and they're splitting this between 100 up to 800 workers, and this is I guess actually 300 machines, okay, and this is the runtime, and you can sort of see it's getting faster as we add more machines, which is kind of nice. This is a little bit of a cheat. A binary tree is a really nice case. So the sparsity is very uniform. Each node just has 3 neighbors. And the way you partition it is also really simple. Okay, it's very easy to partition a binary tree nicely. So this particular problem is a little bit of a cheat, but you know, it sort of illustrates that it does work. So here's another system. So Pregel is, I think, sort of the first and maybe one of the best knowns of these types of system. This is the one that I think is the prettiest. And it's also, the paper I pointed to is nice because it gives a lot of examples of these little programs for a lot of little problems, okay? So the API is a little bit more complicated, but it also makes it easier to express a lot of algorithms. So it gives you a little bit more structure. So you have a vertex and you have an edge, okay? The vertex, like in Pregel, has got an ID. It's got a state that you can change, okay? It's got a list of outgoing edges, and then it keeps track of incoming edges actually 2 ways. One is it's got basically, you know, a hash table that maps from a neighbor ID to the last signal that neighbor sent. And it also has a list of uncollected signals, okay? And then there's a user-defined function called collect, which is intended to somehow access either the received signals or the uncollected signals, the ones that are kind of floating around. There's a user-defined function that will collect those signals and do something, okay? So after you collect, you signal. So signaling is basically, there's a user-defined signal function, and usually what it does is it sends some information out to the edges, okay? All right, so the signal function is on an edge, all right? The collect function is on a vertex, all right? And you know, there's some other extensions, so we'll talk a little bit about how this approach can be done synchronously or asynchronously. So the difference between the received signals being stored as a hash map versus a list of things that have been since the last time becomes more important when you start looking at synchronization. Okay. So here's kind of what the implementation is. So so what does the signal operation do, and what does the collect operation do? Okay. So there's a function that looks like this. So this is really what the process is doing all the time in a simple case where it's doing bulk synchronous processing. You basically go over a certain number of iterations, and you first call signal on all the nodes, first you call do signal on all the nodes, then you call do collect on all the nodes. All right. So do signal basically goes to the outgoing edges. All right, and it adds the signal to the destination of that edge. Okay, so there's a signal associated with that edge, and that gets basically sent to the destination of that edge, okay, the target of that edge. And that gets sent two different ways, one in the map and one in the list. All right. And then you call and when you're doing the collect, you basically just call the collect function, and then you reset the list of uncollected signals because you've now collected them. All right. So this is the basic idea. So it's calling these things e.signal and collect for the state. That's what defines the semantics of those things. Okay. Okay. So when we're done, the next state for a vertex is going to be the output of the collect operation. So that's how the state gets updated. All right. And here, of course, these signals are being just made available for that collect function when you call it. So this is doing a fixed number of iterations, and we'll get around to relaxing that in a couple of minutes. But here are some examples. So this is single path, shortest path, right? So you start off and you initialize everything. So if you're the source state, the distance to you is 0. Otherwise, it's infinity. Okay. Collect, you basically take the minimum of the signals coming in. All right. So those are in a list. Okay. And also the old state. And that's what you make your new state. And then when you signal for an edge, all right, so the signal takes the old source state, the state of the source, and it takes the length associated with that edge, and that's basically what the signal is going to be. That's the signal that's going to be sent to the target of that edge. All right. So whereas a couple of stages back, we basically had to put a bunch of this logic into the compute function. Now, since the compute function is doing something very structured, it's always doing, the collect, and then the signals for all the edges are going to be processed after that. We basically just have to define these three little functions, right? And just to give you an idea how this would work, if this is my source, this would be the initial state, right? And after one iteration, this guy would look at everything that's collected, which would just be the signal from this guy. This guy would look at everything that's collected. This guy would look at everything that's been collected, right? This guy will switch to 1 because that's the min of infinity and 1. This guy is still looking at the min of infinity, so it's not going to change anything, right? And then eventually we'll get to this after 2 iterations. So that's single source shortest path. Here are some other examples. So this is PageRank. Okay, so we're starting with some initial rank value for every node. Maybe that's I guess let's see, what is that? That should be C basically, right? Or C over the yeah, this should be C. Okay, so this is basically the value you get from a reset. When you collect, you basically sum up the signals. So that's the incoming page ranks. You multiply them by this quantity damping factor, which is 1 minus C, and you add it to the base rank, which would be C, right? And that's the new state, all right? And the signal basically is the page rank, okay? So it's the weight at the page rank at the source times the weight of the edge, right? And that's got to be split among all the neighbors. So you also have to look at the total weight So if all the edge weights are 1, this would be just the number of neighbors. Okay. So this is the signal function, and again, just putting these together gives you PageRank. So this one, if you're interested, is Conway's Game of Life. How many people know what that is? Yeah, okay. The rest of you guys, I recommend not looking that up on the internet until you've got a little bit of time to waste. It won't be on any of the tests for this class. So this is another nice one, transitive closure. So what I'm going to do here is I have a graph, and what I want to do is I want to annotate with every node all the nodes that are reachable from that node. Okay, so if I had a graph that was partitioned in a bunch of ways, this might be that was like disconnected, this might be useful. So again, we're going to start off, it's like, well, the only thing I can reach is myself, all right? When I signal, I'm basically saying the edge to the destination. It's like, hey, you can reach this guy. That's the other end of this edge, right? And when you're collecting those signals, you basically say, well, I've got some set I used to be able to reach, and now here are a bunch more things that I can reach. So let's make them add them to that set. Okay. So this is transitive closure. Again, very concise. Here's another kind of nice one. So vertex coloring. So here, the idea is you want to do graph coloring. So every node in the graph has a color which is different from all its neighbors. Okay. An application of this is I've got everybody packed into a classroom and they can all see each other's papers, but I've got 3 different exams to give, right? So I give everybody an exam that's different from his neighbors, okay? So depending on the topology of the room, right? You might need 5. How many different exams, different colors do you need so that everybody has something different from all his neighbors? And how do you do that? Well, it can be complete, but a pretty good algorithm is basically in parallel at every node, see whether it is already right. In other words, it doesn't have any neighbors that conflict with it. And if it does, then you give it a random different color. Okay, otherwise you don't. All right. So this is what the algorithm is. You're basically distributing the colors of your neighbors, right? So if I look at the signals, that's the set of colors for my neighbors. And if I'm in that set, then I choose a new color. Okay, otherwise I don't, right? So this is the simple kind of randomized vertex coloring algorithm, which turns out to be a pretty strong baseline. And this is one other one that I'll skip. Okay. Here's one more example. So this is a little bit complicated, but the idea here is I've got some sort of query. So the guy that did this work is basically sort of a semantic web guy. So I'd like to find a department X that has a member who's a postdoc, okay, and that postdoc received a grant, okay. So I want to find some path X, Y, Z, where from X to Y, Y we've got a membership relationship. From Y to Z we've got a receives relationship, okay. So I'm going to put an empty set at each vertex. Okay, and then I'm going to somehow broadcast this query to everybody. Okay, and the graph is these objects in the knowledge base. So the graphs are things like X's, Y's, and Z's, right? We know if they're departments or if they're people. Okay, those are the 2 types of objects, and their edges that correspond to the relations. Okay, so what do we basically do? So we look at the things that have been successfully matched so far. Those are the neighbors, okay? And we're basically going to split those into things that have been matched or partly matched or fully matched, okay? And if we fully match the query, then we'll say that's a result. Otherwise, we won't. And then when we're done, we're going to say, well, what are the things that we've matched? Okay, so the old state minus the last state I haven't told you about last signal state. So last signal state is, actually, let's skip this. This is a little bit too involved, I think. Here's sort of basically the idea, right? What we're going to do is at each one of these points, we're going to see whether this matches part of the query. All right, so in the query, we basically sort of have a pointer into the query, and that's what we're kind of sending around. We're sending around the part of the query that's been matched. So originally, nothing's been matched, okay? Then at every point, the things that have been matched will be propagated along to the neighbors. So here we notice, well, this query has been matched for department MLD, right? So this MLD node is going to send the partially matched query to its neighbors, all right? And then we can take that partially matched node, all right, and this one, of course, is going to get, this node here might get multiple signals, okay? It might get many partially matched things, all right? Or possibly completely matched things. So if it's completely matched, I say what the answer is, okay? That's the reporting step here. Otherwise, I basically sort of propagate that, okay? So if this one successfully matches with Partha being a postdoc, then I would basically sort of pass that signal along. So that's the basic idea. So it would be basically matching those queries in parallel across a big graph. Okay. So let's talk a little bit about the asynchronous computation. Okay. So the simplest way of doing these graphs in parallel is to just do them in parallel, straight up, no variations. At each point, you update all the nodes in parallel. So that's what is called bulk synchronous parallel operation on graphs. Okay. When you're doing that, you have the old value for the graph, for a node, which has usually been distributed to its neighbors, and you have the new value, okay, which is what you're going to update. All right. That's perhaps a storage issue, because you have to have these multiple copies of a node state. The other thing is there's a potential that this is inefficient. So if you actually had one processor for every node, that'd be fine. But of course, you're not going to have a billion different CPUs, and you might be well working with a billion node graph. So you're going to do this in parallel, but each processor is going to do many thousands of vertex updates. All right. So it might be useful to exploit somehow the fact that, in fact, these things are being done in serial. All right. So if we have two vertices that are not connected, we could do them serially without worrying about the ordering, because we'll get the same result. Okay. The other reason you might care about doing things asynchronously is because, honestly, it might be you're doing page rank, and some parts of the graph have converged beautifully, and they're not changing at all, or hardly changing at all. And there might be some that are still moving around a little bit. So you could update everything at each step. That's perfectly correct. But maybe you're doing some extra work by doing that. So maybe you can save some time by just focusing on updates where there's a big change. Okay. So in signal collect and many other systems, there's a way of basically focusing the resources. Okay. So we're adding two more things to the API. We're going to adding a score for the signal operation and a score for the collect operation. All right. So what do these mean? Basically, instead of just doing all the signaling and then doing all the collecting, well, we'll just do this for we'll do signaling for the ones that pass that threshold, and we'll do collecting for the ones that pass that threshold. All right. So this allows a vertex sort of the ability to say, well, I think it's important to send a signal next time, and I think it's important to collect more signals next time, or collect signals from my edges next time. But that's not necessarily done for everybody. So these are the two new additions. All right. So I don't have in this slide deck examples of this, but a natural thing to do would be to look at how much the node changed. So for example, if you're computing page rank and your page rank at this last iteration is the same as it was before, there's no real reason to send signals next time. Nobody's getting any new information. That's even more true if you're doing something like, say, transitive closure or shortest path. Typically, this tends to be based on the extent to which the value at a node changed. Okay. And here's some numbers. This is basically doing things synchronously, and this is doing things eagerly asynchronously. And eagerly asynchronously is basically you look at a vertex. First, you decide whether you want to signal, then you decide if you want to collect. So you will do a collect right after you do a signal if they're both over threshold. So the synchronous method works a little bit, is indeed slower than the asynchronous method. And to sort of see how much slower it is, you kind of have to look at this kind of horizontal jump, right? But when you have many threads, there's sort of a substantial difference in, there's a difference in the time that you get between these two. All right. So there's some value in doing things asynchronously. Here's another example. So here's another example, which is actually a slightly different strategy for selecting things. So we don't really have to look at these in great detail because this is, again, sort of the one that's fastest, this kind of simple eager thing. But you can imagine doing some sort of more focused strategy where you sort of choose a small number of operations, choose the things that have higher signaling or higher collect scores, and doing those. Okay. So this is another system, and this is the one that's sort of in the assignments. I think it's sort of the clearest presentation that sort of gives you sort of a large number of examples of how you do this sort of processing. So one of the systems that's been more influential in the research community is something called GraphLab. This was started by Carlos Question here at CMU a few years back. Recently sold to Apple for a number of dollars that has, I guess, maybe 8 zeros in it, quite a lot. Okay. So what's GraphLab like? Okay, same kind of story. The data is in a graph. There's a user-defined vertex function. Okay, so there's a little bit different control over the scheduling. So the vertex function can sort of insert new tasks in a queue. The messages have to follow graph edges. Okay, just like in signal collect. Okay, there is a shared table for global data. One thing that was nice about GraphLab is Carlos spent a lot of time building nice library algorithms for things like matrix factorization and CoEM, which we'll be talking about in a couple of sessions, support vector machines, Gibbs, and so on and so forth. So this was like kind of a project which went for a while and had a number of descendants. So the basic vision behind this is that you'd have sort of a rich library of machine learning algorithms. They'd be built on top of a general purpose graph processing API. And you could stick different backends. So you could do your backend graph processing in Hadoop if you had a really big graph, or you could do it in a distributed setting with threads, and so on and so forth. So the idea is that this would be sort of like a way of achieving independence from the kind of particular parallel architecture you want to use. Okay. So let me just talk about some of it. So the original GraphLab was actually quite similar to Pregel and Signal Collect. So GraphLab, I don't have the picture, right? So the original logo for it was Carlos's dog, which was a Labrador. So it's like GraphLab because it was a lab. The dog was a lab. So one of his students came up with a system. So you'd think this would be pronounced Graph Chi, but it's not. It's actually Graph Chi for Chihuahua because it was designed for smaller machines. All right. So what's the idea? All right. So in Graph Chi, here's the key insight. So there's some things in a graph that you can do just by streaming through it. Okay. So like the PageRank nibble algorithm, you just stream through multiple times, so it's pretty efficient. Okay. In general, that's hard to do on a graph. And the problem, of course, is the neighbors aren't all together in the stream, okay? So I can arrange things so like, all the edges coming into a vertex are in a stream, but then I don't see what its downstream neighbors are doing, right? So I can't like easily sort of send its like messages to the downstream neighbors, okay? So, by its nature, those edges kind of go from one place to another. So it seems like, putting the graph on disk and streaming it is just inherently a problem, which is why, of course, you want to get a big cluster and put it all in memory, okay? So the insight in Graph Chi is that maybe it's not quite that bad, okay? Maybe we can put things on disk and organize these things so, even though we might have to do some seeking, maybe it's not too much, right? So this is a very clever idea, okay? So here's the basic idea, all right? So the first step is I'm going to take all the vertices. Well, these are the vertices, not the edges, okay? So I think we're doing PageRank, and the vertices are all URLs. So I sort all the URLs by, their, lexical value, right? So just put them all in alphabetical order. All right. I'm going to construct something that I call a shard, which is just going to be an interval of those. So this is like the first things, ID between 1 and 100, and then between 100 and 200, and so on and so forth. All right. So each one of these things is going to be called a shard. All right. Remember, we're calling it a shard, but this is actually not a parallel system. This is something that would sit on like, one little Mac that just has one little processor. It's just like single processor system. Everything's on disk, not in memory, okay? So we're calling these shards. And we're calling this an interval, okay? An interval is like some subset of these things. So very concretely, these are vertices 1 to 100, 101 through 700, 701 to 1,000. So these are different intervals, okay? And we want to basically put these small enough to fit in memory comfortably, okay? Because we're really actually going to put them in memory and maybe keep a little bit more stuff in memory. All right. So within each shard, okay, I've got all the vertices and I've got all the incoming edges. All right. So all the incoming edges are stored along with a vertex in the shard. Okay, and the incoming edge, and all these edges are sorted by not what you'd think, which would be the vertex ID, right? Okay, the destination ID. In fact, they're sorted by the source ID, okay? So these are all the vertices, these are all the incoming edges that go to a vertex between 1 and 100, okay? But they're not grouped by vertex. Instead, they're sorted, okay, by the ID of the node that is connecting to that vertex. So they're sorted by source, and their destination is all between 1 and 100. Okay? Why would you do that? It's a weird decision. Okay? Well, this is because what you really want to do is you want to stream through the data, and at each point in your stream, you want to have all the edges that go into a vertex and all the edges that go out. All right? So what we're going to do is we're going to take this thing and load it all in memory. Okay? It's small enough it fits in memory. Okay? So that's all the incoming edges for this set of 100 vertices. Okay, now I just got to get all the outgoing edges, all right? And because of the way I've sorted, those outgoing edges are grouped together in shards, right? So the outgoing edges that happen to go to a vertex between 101 and 700 are going to be in this shard, and they're all going to be together because the edges here are sorted by the source ID, which is here between 1 and 100. So all the source IDs between 1 and 100 are going to be together, right? And the same thing here and the same thing here. Okay. So yeah, they're kind of scattered on disk. Okay. But they're not completely scattered, right? They're basically scattered in p minus 1 places. All right. So that's not so bad. So what we're going to do is we're going to load all these edges in memory. Then we're going to jump to this point in the disk, and this point in the disk, and this point in the disk. Okay. We'll read these things. And while we're doing that, our like clever little disk driver, which is used to people streaming through things quickly, is probably going to say, well, I think I'm going to like load like a little bit more stuff here, a little bit more stuff here, and a little bit more stuff here. So it'll buffer the things that it thinks we might be getting to next. All right. And lo and behold, what happens next is we're going to be done with this thing. We're like done all the processing for those edges. We've got the incoming and outside. So now I'll load all this in memory. Okay. And now what I'm going to be basically doing is going to those next intervals, right? We're going to these other outgoing blocks in memory and all the other places on disk. Okay? So we're not doing a straightforward streaming. We're really keeping p different positions into the file. Okay? If you think about the number of reads we're doing, then you can see what's basically going to end up happening is that in this process, what you're going to be doing is you're going to be doing p reads for each shard. So you'll be doing p squared reads to do one full pass through the data. Okay, so it's way worse than p. Okay, so it's not streaming, but you only got one little machine. Okay, so it turns out this is actually surprisingly efficient. There's a few other little tricks behind this that I won't talk about too much. I guess the main thing to notice about this is that when you're updating things, you're updating them on disk. Okay, so there is in fact no synchronicity here. Everything sort of has to be asynchronous. As soon as a node's value gets changed, it's going to be visible to its neighbors. Okay, so it's an asynchronous processor. Okay, but it turns out to be pretty reasonably good performance. So this is on a ordinary desktop, a Mac Mini. Okay, and these are a bunch of problems where there are tens of millions or billions of edges. Okay, we break them into a certain number of shards, maybe something like 20 or 50. Okay, and there's a certain amount of pre-processing time to do this. Okay, but once you do this, the performance is actually pretty good. So so this is GraphChi on one Mac Mini, doing PageRank on a big problem. Okay, this is doing matrix factorization on a big problem. All right, this is the Netflix data that we talked about doing the other week. All right, this is triangle counting versus Hadoop. So triangle counting is something you do in computing the clustering coefficient for every vertex in a graph. So here it's actually much faster than a published Hadoop system. All right, here is belief propagation on a graph, which is sort of a PageRank kind of computation. So here's some. So those are basically the results for GraphChi. So it's a cool system for doing this graph processing thing. The nice thing about it is it has an API that's very simple to GraphLab, but you can sort of try things out and do them just on a small machine. All right. All right, I've got two more things I want to talk about. And these are also both GraphLab descendants. So one is called PowerGraph. So PowerGraph is kind of aimed at the other end of things. So GraphG is for sort of moderate-sized graphs that you could imagine doing processing on one machine. So Power Graph is for really big graphs. So a really big graph you're going to store in memory. It'll be stored in memory on a cluster. And remember, as I said before, you'll be basically partitioning the data across the cluster. And when you do that, there's going to be big differences in the communication time. So communicating from vertex to vertex within a single worker is cheap. Communicating across two different workers is going to be expensive because it's going to be going through the network. Okay, so so this is a problem when you get, so this can be a problem, all right. So a lot of graphs follow this power law distribution that we mentioned earlier, okay. So if you look at the degree distribution, you often see something like this. So what does that mean? Whoa, what does that mean? So what it means is, in this particular case, if we look at these very large degrees, like a million, some number of billions, there are in fact, a handful of nodes that have, each of these very large numbers of degrees. There are lots of nodes, lots and lots of nodes that have very small degree. Okay, so there's tens of millions of nodes that just have a few neighbors. So kind of, if you take a look at a typical node, it's going to be very sparse. But there are a handful of nodes that have lots and lots and lots and lots and lots of edges. All right? So what does that mean? Okay. That means if what I want to do is partition those edges so that I've got one vertex and all its edges on one machine, I mean, that's fine for almost all the edges in the graph, for all the vertices in the graph, because most of them, the number of the neighbors is very sparse. But there are a few where the number of neighbors is very large. So those aren't really going to fit. You're not going to be able to put those on one machine, right? If you did put them in one machine, you still are kind of got a problem. Because you're doing the processing in parallel across the edges, but you've got some loop over the signals or the neighbors, right? So for most of the nodes, again, that loop is really fast, right? You're just checking a few neighbors of a node. 10 or 15 or 20, it's a quick loop. For a few of them, it's tens of millions. So if you do it bulk synchronous, then there'll be some steps that are, the loop iteration count is going to be 10 million, and most of the other ones it's going to be 10. So it's very unbalanced, okay? And it's going to cause a lot of message passing. Okay, so this is basically sort of the problem. So here's the solution. So the basic idea is we're going to replicate data across different parts of the graph. And we're going to use a slightly different API, which they call gather, apply, scatter. Okay, so roughly the gather is like a combiner. The apply is kind of like the vertex-centric compute process. Okay, and the scatter is like the signal, so it's sending messages to the edges. All right. So this is PageRank. I'm sorry, we changed the notation, but it's the same algorithm. Okay. Here's the program. All right. So we're going to do two things. First, we're going to gather. Okay. So so for every message from J to I, so these are all the incoming links for I. Okay. We're going to produce this quantity. All right. But the gather kind of goes into two different pieces. Okay. So there's a gather for the edge, and there's a reduce process that will collect those things. All right. And then there's an apply function, which is basically going to compute the new value like that. All right. And then finally, we're going to scatter. Okay. So this is basically deciding what edges are going to be active. All right. So it's a lot like signal collect with this additional sort of combiner process. Okay. So this gather sum step is really like a group by and then reduce. And together they act like a collect operation. All right. The scatter thing is like the signal operation in signal collect. All right. So I didn't change their notation for the page rank because they have these lovely animations for what you do. All right. So here we've got our vertex Y that's got 10 million edges. As you can see, there's 10 million, 1, 2, 3, 4, all the way around. Okay. So it's a really big, high fan-out edge. Okay. So rather than put it on one machine, I'm going to split it. Okay. So there's multiple copies of Y on different machines. Okay. So first we have to gather all the signals. Okay. So on each machine, first we locally gather the signals. Okay. And there's a sum step. Okay. But like I said, this is actually like a combiner step. So first we do that combination locally. All right. Then we do it globally across the network. Okay. So the gather step, we're basically collecting, but we're doing it in 2 stages in a kind of MapReduce framework. So now I've got this, this summation. All right. Then we're going to apply. Okay. So we're going to recompute the page rank here. Okay. And once I've done that, I have to broadcast it across the network again. Okay, so I've got to send that new information to all the replicates. Okay, and that's also handled, that's sort of handled in the sort of underlying system. And then finally, we scatter. Okay, so we figure out what the neighbors are, and of course, there are neighbors on every machine. Okay, and those are the things that get activated the next time around. So this is the basic idea. Signal collect with combiners. The other thing that they looked at in Power Graph is there were, and as far as I know, these were like sort of the first things they did some kind of systematic experiments of how you partition the graph. So what you'd like to do is you'd like to partition it so that the number of shared nodes is small. Okay, right? So you'd like to have a small number of duplications. Okay, so this is a graph processing algorithm. It's called vertex cut. It's NP hard, but power law graphs should have good vertex cuts, and there are many good vertex cuts in a power graph. So they looked at a few different things. So since there are lots of good vertex cuts, you could just try doing it, cutting things randomly. So it's really cheap to do that. Okay, this is the average partitioning of a node. Okay, this is doing it using something more like a kind of global partitioning algorithm. This is something which is sort of greedy, locally greedy. So that's like sort of a compromise between these two. And sort of what you'd kind of expect. The greedy algorithm, which looks at everything and it's the slowest to build the graphs, actually gives you the best partitions, and it's fastest in terms of the runtime. But you also get sort of reasonably good speed-ups over random by doing these kind of simple, cheap heuristics. Okay, so that is Power Graph. Okay, so that was really sort of the big spin-off that got sold to Apple. But there's another very cool system that came out of this, in addition to GraphG, that you may someday want to use. It's called GraphX. So it's done by Joey Gonzalez, who I guess was a student with Carlos, and he went off to do a postdoc with the Spark people at Berkeley. And what he basically did was he re-implemented GraphLab in Spark. So he came up with some kind of clever ideas where you could do the basic operations that were used in GraphLab and just build it on top of Spark. Okay. So there are lots of obvious reasons why you want to do this, right? I mean, lots of people are working on Spark, so get nice stable systems to work on. You might do like your data preprocessing in Spark as well. But there are also some constraints. So in Spark, I don't know if you remember this, but they have this notion of a resilient distributed data set. So a resilient distributed data set is like a sharded Hadoop file, and it's considered an immutable structure. You can read it, but you can't write to it. Okay. We're going to use RDD to encode graphs, so they're called RDGs. But that basically means you can't write to a graph. So that's a really different, that's a really big change for this paradigm. So originally it started out saying, well, the whole idea is it's mutable, you can change the vertices, right? So why does this even make sense? So the idea is basically we're going to take the graph and we're going to partition it so that even though we're changing some things, most of the graph doesn't mutate, right? So if we're changing most of the time is some property of a vertex, like maybe it's page rank. So we have one table which has the properties of a vertex, okay? And then we have another table which can have properties of an edge, like its weight or so on. And the key idea is when we're doing something like PageRank, we'll be constructing a new vertex property table, but we won't be changing the actual connections, the edges. So this will be the big part, this will be the small part. We'll just, we'll be not mutating the small part, but we'll be updating the small part. So the idea now also is to make sure that the operators that we implement, the high-level operators, will take advantage of these original structures. Okay, so there are lots of things that you can do, which obviously we can do any, Spark operation on these tables. The ones that are kind of specifically for graphs are these, okay? So a graph basically has a vertex table and an edge table, okay, right? So, we've got an ID and then the properties of the vertex, and then we've got a pair of IDs and then the properties of the edge, right? So this is how the graph is stored, all right? There are a couple of different ways we can process it. We can sort of get at the underlying tables, right, of vertices and edges. You can also get another underlying table. So this basically gives you an edge together with the source and destination vertex data, all right? So this is a bigger copy of the edge data, if you like, all right? You can do some transformation, so this reverses the direction of all the edges. You can construct a subgraph. You can alter the vertices or edges with a map. We can do some join operations, okay? So we can take another vertex table or another edge table, and we can sort of combine it with the one we've got. And then there's one other operation. So this is basically kind of a low-level processor, which is used to do this kind of scatter, gather, apply stuff. Okay, so there's one map function, which basically goes from an edge table here, so a vertex and an edge pair. Okay, so this is a source, and this is a node, and this is an edge leading away from that node. Okay, and then this gives you a list of other vertex IDs plus some other information. So this is the message you're going to be sending there. Then there's some sort of reduce, so this is kind of the gather step, right? And that could be used for a combiner as well. And then this gives you a new graph where this is the new set of vertex information and the same edges, okay? And of course, we're doing structure sharing here, so we don't copy those edges. We just kind of keep them. All right. So this is kind of the low-level routine. There are some other routines called aggregate neighbors and aggregate messages, which are used sort of to supplement this. But that's the basic idea. And I won't go through how you can implement these things, but the basic story is the operations in GraphX are sort of a few thousand lines in Spark. Okay, and then implementing Pregel or GraphLab is just a few dozen lines in GraphX. So it's pretty close to GraphX, to GraphLab, right? It's pretty close to Pregel, right? And then, all of these things are fairly concise to write. And I guess there are a couple of things that Joey wrote sort of directly on top of GraphX. So I'm not going to show you all these lines of code, but just sort of gives you an idea. So how does this work? Okay. So what we did was we started off with this highly tuned system that was designed just for this architecture, GraphLab. And we replaced it with something that is built on top of a lower level abstraction, or a low we built it on a lower level system. It was really designed for other purposes. Okay, so there are really two things that could happen. One is it could have been much better because the lower level system is, really well designed and, very stable, and it's got all sorts of optimizations that Carlos and his team didn't have time to do in GraphLab. Or another thing is it could be much, much slower because it's just really basically a poor match. So it turns out it is slower, but not too much slower. So for PageRank, it's about 3 times as slow. And just to sort of kind of calibrate, that's still much faster than Hadoop, much faster than using Spark without using the GraphX packages and the kind of optimizations that they suggest. I mean, obviously, this is Spark, okay? But writing things in GraphX leads to a faster iteration. Giraffe is an open source Apache kind of Pregel copy. So for this task, it's about 3 times slower, which is sort of not too bad. And that sort of tends to be the story. It tends to be about 2 to 3 times slower than the GraphLab system. All right. So I'm going to wrap up now. I don't have much more I want to say. So the summary here. We've talked about a bunch of things that basically use large immutable structures on disk, distributed structures on disk, okay? So, really almost everything we talked about. Hadoop reads in a file, writes out a file. We also talked about Spark, which basically has these RDDs. Those are immutable structures as well. They're backed up on disk, but they can be cached in memory, distributed memory, okay? And since they're cached the same way that, since they're partitioned the same way that a distributed file is, there's not really any complexities in how you distribute them. So this is an in-memory structure. So it's faster to loop over, but it's not different in any other kind of fundamental way, right? We've also talked about some large mutable data structures, okay? So Pregel, GraphLab, all the things I talked about today, the structure is a graph. So you've got a single mutable graph that's stored in distributed memory. A little bit later, we're going to talk about another distributed data structure called a parameter server, where you basically kind of have a hash table that you're distributing in memory and using that to communicate with workers. For the graph-based systems, there's a lot of small differences in the API, okay, but they kind of have a similar flavor. A typical algorithm will basically update the vertex state, and then changes in state are going to be communicated by messages. That's kind of the flavor of all of these things, and then sort of the details of how they do it. Some of them do it a little bit more elegantly. Some of them do it a little bit less elegantly. Some of them have spent more time looking at different computational issues. But they're all sort of doing the same sort of process. So the big wins are cases where the graph stays the same, but the vertex data changes. Okay, so things like PageRank are prototypical. We're going to be talking about a bunch of other algorithms that are learning algorithms or label propagation algorithms. So these are semi-supervised learning algorithms that work on graphs. And a lot of these have this same sort of property. They're a little bit more interesting to talk about than PageRank. But these are all things that are kind of good candidates for implementing in this sort of way. And most of these things are designed for graphs that are small enough to fit in distributed memory. That's where with the exception of GraphG, that's sort of the sweet spot for them. Okay, so that's it. Just a few kind of high-level things to kind of take away. So GraphX has got the big advantage that it's tightly integrated with Spark. GraphQL has a nice advantage that it runs on a regular machine. Okay, so GraphLab is high performance, but not free. These other ones, I think down here, are sort of like less widely used. Pregel is something that, as far as I know, is still used at Google, but not really used outside. You know, again, the kind of things important to think about is basically what's the architecture that these are meant to run on, right? How do they store the graph? How do they distribute the graph? How do they partition it? And also whether the processing is synchronous or asynchronous. So in practice, asynchronous processing is also often fine. Mathematically, it's often harder to show something about an asynchronous version of an algorithm. So you're maybe bound to do a little bit more experimentation if you want to use an asynchronous system. So that's basically it. So another day with early dismissal. I guess I'll see you guys Tuesday, and I'll stick around here for questions. Okay.